Today's lesson is about arithmetic series. It's similar to arithmetic sequences. However, each term is being added together, so you're looking at a sum rather than just a list. So remember, a sequence was a list. A series is a sum. So each term in the list is being added up. Because they're both labeled as arithmetic, they're both going to have that property where there's a common difference. So let's say this was our sequence. It's an ordered list of numbers because it's a sequence. We would notice this sequence was arithmetic, little review, because there's a common difference of +2 between each of the terms. So as a series, all that would change is that it wouldn't just be a list of terms, it would be the sum of these terms. If I wrote the list this way, this is an infinite series that continues without end. You can see that word listed in our vocab. If I wanted it to end, there would have to be a distinct place that it ends, as I've written here. Okay, notice that after the 9, there's not a ... so that would be finite. So a series has a sum. If it's arithmetic, you still have a constant difference between terms like you did with your sequence. Finite means it has an end, and infinite means it does not. Sometimes, to denote that they want you to use a series, or they want you to be summing or adding things up, they use something called summation notation. Okay? So it's the letter sigma. I don't like the way that one looks, so I'm going to redraw it. Okay. And normally at the bottom of sigma, they'll have a variable and they'll set it equal to a number. That's the number you start plugging into your rule. Then at the top, they'll have another number. That's where you start. And then after the sigma, they will list the rule that you should be using. So in this case, we're going to use the rule 2n plus 1. Okay? So this is our summation notation. Okay? It uses sigma. Now, what this really means, if you write this out, this means you take that n is equal to 1. You plug that in to the rule. So 2 times 1 is 2 plus 1 is 3. 3 is the first term of your series because it's what you got by plugging in the first thing they said to plug in, which was 1. Then what you do is you continue to plug in the next number. And what I mean by the next number is the next integer. So in this case, 2 comes after 1 in the world of integers. So the next thing we would do is plug 2 into our rule. 2 times 2 is 4, plus 1 is 5. And then we will continue in this way until we get to the number they've listed at the top of sigma. That's the last number we'll plug in and we'll stop. So we still need to plug in 3 and calculate this. 6 plus 1 is 7. And then we need to plug in 4. Now this bottom line where I'm plugging everything in, I'm doing that specifically to show you guys. Once you get good at this, you wouldn't have to show each of those. So this is your series that you see right here. So this is the sigma notation for the series, and then the series actually listed out. You can see that it's finite because there's a number listed up here, which means it ends. So we should be able to add it up, and we can just add up the terms. So 3 plus 5 is 8, plus 7 is 15, plus 9 is 24. All right, so now what we want to do is think about if you had a list of 20 numbers. It would be harder to add them up, so we want to be like Gauss. He's the guy you read about in your Canvas assignment. And what we want to try and do is find a quicker way to add up these numbers. So let's say we wanted to add up the numbers from 1 to 20. What Gauss did is he noticed a pattern that the first and the last term added up to the same amount, so as the other term. So like 1 plus 20 is 21, and then 2 plus 19 is also 21. 3 plus 18 is also 21. So what's going to happen is we're going to continue pairing the numbers up in this fashion until we get to some place in here where it's like the middle, and the last little pair, in this case 10 and 11, would take place, and they would also add up to 21. So what's happening here is 1 plus 20 or 19 plus 2 or 18 plus 3, whatever, those ended up being added together, making 21. If we're adding up the numbers from 1 to 20, then when we look at this whole list, there are 20 items there. So we could say we're using the 21 20 times, but that would be wrong because each number itself was not 21. It was being combined with another number in the list to make 21. So actually, we should cut that in half. We're only using 21 half as many times as the number of terms in our list. Okay? And we could look at a more complicated version of this too. Say we were adding up the numbers, say we wanted to count by twos. Say I wanted to add up this list from 2 to 24, counting by twos. We can still see a same pattern arises because it's arithmetic. 2 plus 24 is 26. 4 plus 22 is 26. 6 plus 20 is 26. Okay? So again, we're getting 26 because that was 2 plus 24 or 4 plus 22, however you want to look at it, we're getting 26. How many times we're going to get that 26? Well, from 2 to 24, counting by twos, we would have to figure out how many terms that is. 10, 12, 14, 16, 18, 20, 22, 24. So that is 12 different terms. But again, we're not getting 26 all 12 of those times. They're being paired up, so that would be cut in half. So notice there's kind of this process we would go through each time. So now if we use a little bit of notation, okay? Notice in both cases, things are being divided by 2. Okay. What's being divided by 2 are these two things multiplied together. Okay. Remember that our 20 came from the number of terms that was in the list from 1 to 20. 12 is also the number of terms that was in the list from 2 to 24. And in our series and sequence notation, the number of terms is calculated by n. Okay? So that's where the 20 and the 12 are coming from. Now, in this problem, we had 21, which was coming with 1 plus 20, or several other places. In this problem, 26, which was 2 plus 24. Notice in both cases, that's the first term plus the last term in the list. And remember that in our notation, we would note that as the first term plus the last term. Now, since in different times we'll be adding up different number of terms, we'll put a sub n as the last term because n is the number of terms. So if it's 10 terms I'm adding together, I'll add up the first term and the 10th term. Okay? So let me formalize this a little bit more. This is what you want to write on your paper. To find the sum of an arithmetic sequence, to find the sum of an arithmetic series. So S we just used to denote sum. The little n is telling you the number of terms. And the way that you see the formula written in your book is like this. Okay. So remember, n is how many terms? A sub 1 is the first term, and a sub n would be the last term or the nth term that you were adding up. So now we can go do some problems. Here's an arithmetic series. So first we want to find the sum of the first 40 terms. So we're finding this. Okay. So according to our formula, that means there are 40 things being added together. We're going to divide that by 2. And we want to multiply it by the first term plus the nth term, which in this case would be the 40th term. So from the list, I can see that the first term is 3, but I don't have the 40th term. So I have two choices. I can either write out the series until I get to the 40th term, or I can use what we talked about last time, that there's a rule that helps me find the rule for anything, and that can help me find the 40th term. So the first term is 3. And the common difference in our series is 5. So the rule rule for this series is 5n minus 2. Again, my whole point in doing that was really to use the rule to find the 40th term without having to write it all out. So 5 times 40 is 200, and 200 minus 2 is 198. So now I'm going to finish this calculation. So this was all kind of work off to the side to get this one piece right here. So 3 plus 198 is 201. So I'm going to multiply that by 40 and divide by 2. Which gives me 4,020. So if you add up the first 40 terms of that series, you'll get 4,020. Okay. The second problem says to find n when you know that the sum is 570. So the first thing I know is that it should be less than 40 because I just found out in part A that the sum of 40 terms would be 4,020 for this series. 570 is much less than that, so I should get something less than that. So let's see here. 570 is the sum. I actually am finding n, so I don't know how many terms that is. I know the first term is 3, and I don't know the last term. If I knew the last term, I would know how many there are, maybe. So this is a bummer because this one formula or this one equation has two different variables in it. But again, I want to remind you of the rule. The rule says this. And I'm not going to go through writing the whole thing again for this series because you already did it over here. So we know for this case that the rule says this. A sub n equals 5n minus 2. So what I'm going to do in this case, even though I don't know what n is, so I can't make this a number, I can substitute a sub n. I can make it equal to 5n minus 2. So that's what I'm going to do here. So now I'm going to have 570 equals n over 2. And when I simplify what's in this parentheses, I get 5n plus 1. I'm going to multiply both sides by 2. So I get 1,140 equals n times 5n plus 1. And I have a quadratic on my hands. So I'm going to go ahead and simplify this quadratic. So I get 5n squared plus n. And I want to set it all equal to 0. So the next thing I would do is I would try to see if this factors. Okay, so like I said, we want to factor this. So it obviously takes some time. I did it off on the side. If you're struggling with that, you can look at it. It's kind of a big factoring problem. But it does factor as 5n plus 76 times n minus 15. So if we set 5n plus 76 equal to 0 and n minus 15 equal to 0, we get that n can equal 15 or n can equal negative 15.2. This is not an okay answer, the negative 15.2, because remember, n is supposed to represent the number of terms you're adding up. You can't add up a negative number of terms, and you can't add up 0.2 number of terms. So the only acceptable answer we have here is that n is equal to 15. So 570 must be the sum of the first 15 terms of this series. All right. We're supposed to find the first 3 terms of an arithmetic series in which we know the first term is 5. So we're looking for the first 3 terms. They told us the first term is 5. I'm going to kind of leave this for my solution. They also told us the last term is 100 when the sum is 1,050. So using our sum formula, if 1,050 is the sum, we don't know how many terms that is added together, but that's the first term of 5 plus the last term, and the last term, the a sub n, when the sum is 1,050, is specifically given to us as 100. So we have this equation. I'm going to multiply both sides by the reciprocal of that fraction to get n alone. I can see that 105 goes into 1,050 10 times. So this is the sum of the first 20 terms. That does not help me with the answer to this question. I don't know the first 3 terms. How to get term number 2 and term number 3 would be if I knew the common difference to add in there. So now that I know this is the sum of the first 20 terms, I'm going to use the fact that they gave me this, and that I now know that's for 20 terms, that tells me that the 20th term is 100. It's not just the last term they added up. I now know it's the 20th term. So the reason that helps me is because if you remember, again, we have this rule. Okay. And if I specifically use it for when n is 20, I would have that the 20th term is equal to the first term plus the difference times 20 minus 1. Because remember, I'm plugging in 20 for n, the 20th term. Now I actually know the 20th term. It's 100. And I actually know the first term. It's 5. 20 minus 1 is 19. So now I have a simpler linear equation. If I subtract 5 from both sides, I'll have 95 equals 19d. And then if I take 95 and divide it by 19, I have that d is equal to 5. Now that I know that the common difference is 5, I'm going to add 5 each time to create the next term in my sequence. So the first term was 5. 5 plus 5 would be 10. So 10 will be the next term. 10 plus 5 would be 15. So 15 will be the last term. All right. So now we're going to go ahead and find the sum of each of these series. Oops, I'm sorry. Go back one. Okay, so notice these are written in sigma notation, but we can still use our sum formula to help us find it if we don't want to write out all the terms. So for the first one here, I know that it's arithmetic because look at the rule. Okay? The rule looks like the equation of a line. It also does in part B. And we talked about how the arithmetic sequences have that common difference that's like the slope when we looked at our cup data. So I know that this is arithmetic, so I can use for both of these problems this sum formula instead of doing what we did on the very first slide, which was write out all the terms and then add them together. Okay? So in the first one, if I'm summing from 1, plugging in 1 to plugging in 8, that's 8 terms because 8 minus 1 is 7, but that didn't account for the 1. So I have to add one more on there, so there's 8 terms. So in this case, I am adding up 8 things. The first thing is the directions of what it says to do first. The bottom of the sigma says n is equal to 1. So the first term is going to be taking the rule and plugging in 1, which in this case would come out to be 5. The nth term in this case will be the 8th term. I'm saying that because 8 is at the top of the sigma, therefore that's what we plug in to get our last term. And so in this case, I'm going to take the rule and plug in 8, which gives me 19, and 19 would be my last term. Now I have everything I need to plug in to get the sum of the first 8 terms. N is 8, the first term is 5, and the nth term, or in this case the 8th term, is 19. So this is the sum of 8 terms. This is going to be the same as 4 times 5 plus 19, which is 24, which means the sum of the first 8 terms in this case would be 96. Now you could have written out all the terms, and you could have added them up like we did on the first slide. That's fine. It might not even be any slower in this case. However, if I asked you to sum 100 terms, that would definitely be a rough way to go. Okay? All right. So we're going to look at the next one as well. You see the next one ends with 12 and starts with 4. If you do 12 minus 4, that's 8. But remember to add 1 back on because when you subtract, it doesn't count that beginning step. So this is actually 9 terms. So n is equal to 9. The first term in this case, when you look at the directions right here on the sigma, it says the first thing you're going to do is plug in 4. So we're not going to plug in 1 to find out what the first term is. We're actually going to plug in 4. So I'm going to take my rule and plug in 4. 8 minus 4 is 4, so my first term is 4. Okay. My nth term, or in this case it will be my 9th term, but notice the number on top of the sigma is what we get by plugging in 12. So we're going to take our formula and plug in 12. 8 minus 12 is negative 4. So now we have there are 9 terms. Our n is 9. Our first term, which according to the directions we plug in 4 to get that, is 4. Our nth term, or our last term, which according to the sigma notation we plug in 12 to get that, is negative 4. And now we'll plug those things into the formula. Now I am finding the sum of 9 terms, even though the number 9 was not one of the numbers we plugged in. Remember, the first term was 4. And the last term was negative 4. Okay. So in this case, we get 9 over 2, or 4.5, times 0, which will just be a sum of 0. Now, that might seem a little bit odd, but if you look at this problem, you're summing numbers, and as you plug it in, if you plugged in, notice when you plugged in 4, you got 4. When you plugged in 5, you got 3. When you plugged in 6, you got 2. 7, you got 1. 8, you got 0. Then if you plugged in 9, you got negative 1, negative 2, etc. So what's happening is a lot of these will be canceling each other out as we're adding it up. Since the series is going down, it's okay that there's a place where the sum is equal to 0. So the homework that goes with this is going to be homework number 2. If you have time tonight and you would like to start that homework, you can. Otherwise, it'll be assigned to you tomorrow night. We'll answer any questions that you had on this in class, and then we're going to start working on something else as well.